Deep dynamics models for learning dexterous manipulation. Dexterous manipulation with multi-fingered hands represents a grand challenge in robotics. Although some real-world tasks can be accomplished with simple parallel jaw grippers, there are countless tasks in which dexterity is critical. This first task involves rotating a 1 degree of freedom valve to arbitrary goal positions. After just 20 minutes of training, we see that our model-based approach is already good at nearby goals. This task provides challenges such as planning in high-dimensional nonlinear spaces, as well as contacts between the fingers and valve. We compare our method to soft actor-critic, which is a state-of-the-art actor-critic method, as well as natural policy gradient, which is a state-of-the-art policy gradient method. Although all methods succeed at this task, our model-based approach is 20 to 50 times more sample efficient. This next task is in-hand object reorientation. Manipulating free-floating objects involves the challenge of dealing with contacts, as well as the abundance of terminal states, which can cripple an agent's ability to navigate high-dimensional convoluted spaces. Successful manipulation also requires careful stabilization strategies, regrasping mechanisms, and finger coordination. Here, we see all three methods succeeding at performing 90-degree rotations of the cube, as they were trained to do. Note, however, in this plot of performance versus sample complexity, that our method is still approximately 20 times more sample efficient in achieving this reorientation success metric. If we instead test the methods on performing rotations that were not seen during training, we see that both soft actor-critic and natural policy gradient are unable to do so. Our method, on the other hand, is indeed able to better generalize to these new rotations and succeed at the task. This next task involves rotating 2 Baoding balls in the palm to follow the desired circular trajectories, shown here by the red markers. While manipulating one free object is a challenge, sharing the compact workspace with other free objects further exacerbates this challenge. Here, we see that even with a large amount of training data, both natural policy gradient and soft actor-critic get stuck in local minima. The inter-object interactions make this task quite challenging for even these state-of-the-art model-free reinforcement learning algorithms. Both of the balls need simultaneous coordination, and inconsistent movement of either one ends up knocking the other out of the hand, leading to catastrophic failure. Our method also experiences these inter-object interactions and manipulation challenges during its training. However, unlike the other methods, our method is able to successfully learn this task from scratch. Furthermore, it does so using the equivalent of only 2 hours of training data. This performance plot shows that our method not only succeeds, but it does so with very little data. Note that even when we explicitly try to lower the risk of local minima by prescribing spread-out initializations of the ball locations, soft actor-critic and natural policy gradients still fail. In addition to sample efficiency, our method provides further benefits in the form of generalization. Here, we see that the same model that was trained on the Baoding task can be applied at runtime to other tasks, such as moving a single ball to a desired location, or rotating the Baoding balls clockwise instead of counterclockwise. This next task of handwriting illustrates the difficulty of tasks that require precision. It requires precise maneuvering of all joints in order to control the movement of the pencil tip and enable legible writing. Furthermore, the previously mentioned challenges of local minima, abundant terminal states, and the need for coordination still apply. Here, the green dot shows the desired trajectory. We see that when these methods are trained to execute a single fixed trajectory, they all succeed. Note, however, that our method is still 40 to 80 times more sample efficient than the model-free algorithms. Next, if we try the more interesting task of training on arbitrary writing trajectories instead of just a single one, we see that both soft actor-critic and natural policy gradient fail. Our method, on the other hand, can learn to successfully and precisely write arbitrary trajectories. We see that our method not only succeeds, but does so using very little data. We also compare our method to these two prior model-based methods. We see that they too, like the model-free methods, are unable to escape local minima and succeed at this task that requires precision, coordination, and versatility. Finally, we show that our method can not only write arbitrary trajectories, but that same model can also be applied at test time to write new characters or digits, as shown here. In summary, our model-based method succeeds on these challenging dexterous manipulation tasks that require generalization and versatility. Furthermore, it outperforms existing state-of-the-art methods, and it does so using less than 2 hours worth of real data.